I bought something online from a company called JLC PCB. They're printed circuit boards for a macropad vision mixer I've designed. A vision mixer is what's used in live productions to select and mix video feeds. This one here is a Roland V800 Mark II, which I use to mix my school assemblies. I want to make my own one of these, but in a way that won't put my bank account into the negatives. In the case of most vision mixers, the video processing is done inside the switcher, but that makes them much more expensive. I want to use OBS, which is a free open source broadcasting software, which has a surprising amount of features. To use OBS, I need the mixer and the computer to communicate and tell it what to do. There are a few ways to do this. I could use MIDI, which is a standard used by almost all musical instruments and many vision mixers. However, to do this, it would require custom software or OBS plugin, which makes the mixer a little bit less compatible. I ended up just using the HID, Human Interface Device, capabilities of the microcontroller I picked to send out keyboard shortcuts which I can program to be anything. That means I could program it to work in DaVinci Resolve for multi-camera editing, or map it to camera presets for a PTZ, or use it in OBS. But how does it work? I designed these over a few days using KiCad, a free PCB design software. I also had to model the key switches and footprint, which I did in Onshape. The brains of the mixer is a Raspberry Pi Pico, and I designed the PCB so I could simply solder the Pico to it. The switches are key switches with individual LEDs. Each switch has a 10k pull-up resistor and a 220 ohm resistor to protect the 1.8 volt LEDs from the 3.3 volt of the Pico. The switch has a 3.3 volt in, which when pressed goes through this pin, through the 220 ohm resistor and into the LED. This pin is connected to the pin in on the Pico and ground through a 10k resistor. An annoying thing about these switches, which I only learned after I bought them, is that there's only one normally open pin, meaning on when pressed, which is used for the LED. The only other pin, other than the always on pin, is on when not pressed. Because of this, the Pico button logic has to be reversed. Now this should be fine until there's a failure of the switcher. If a connection is broken, the Pico will register it as a button press, meaning instead of the button not working when it breaks, you have a button that is stuck down. This should be fine as I can always unplug it, but if I were to make this again, or wanted to use something like this for proper events, I would design it differently. I would change each LED to have another pin to itself. This would free up the normally open pin on the switch and would allow me to program the LEDs to light up for preview and program channels just like on most mixers. Now you know how it works, let's go back to the PCBs. The first problem I had is when I tried to mount the switch onto the board. I found out the holes were off by a millimeter. Turns out the switch documentation was not to scale. To fix this, I chopped off the unused pin and plastic aligning posts on each switch. I then drilled a hole on each mounting point on the board so that the switch fits. I just had to make sure that I used solder to bridge the gap from the pad to the newly drilled hole. The next problem I had was the LED holes were also misaligned. To fix this, I just bent each leg of the LED into an S shape. Now all that's left to do is to put it together and solder it. It took a few hours of testing to get it working. Turns out I can't count and only soldered 6 pins on one side instead of 9. During the testing process, one of the traces broke, which I fixed using a cut-off leg from one of the resistors. I also bridged the switch in the top right corner so that the LED is always on, acting as a power indicator. Now it's onto the programming. It's a fairly simple program that just detects when a button is pressed, identifies what button it is, and then sends out the keyboard shortcut for that key. Currently it's set up in a 6-channel mode, which means that the top 6 keys control what's live and the bottom 6 keys control what's on preview, with the 2 buttons on the right being for cut and auto and the 2 top keys on the right being for whatever you want. I also made code for a 12-channel switcher which uses all 12 keys as previews, and you just use the cut or auto to switch between them. And that's it for the programming. At this stage, my friend had printed out a custom housing for it. I modelled the housing in Tinkercad, which is basically just baby's first CAD, as I was too lazy to learn how to use Onshape properly. Because of this, and because I've never 3D printed something before, all the tolerances were off, so I spent about 4 hours meticulously filing and sanding the housing to make the keys and board fit. I used some superglue to fill in some deformities and sanded it flat as well. After that, I countersunk some M3 bolts and cut them to length to hold the board into place. I found some plastic screws to secure the housing shut, and with that all that was left was to paint it. After painting it, I came to the conclusion that the little pieces of plastic in between the switches were making it too difficult and unreliable to press them down, so I just removed them and put it back together. Let's have a look at the final product.